I didn't try to eat it. That's why it's work.
Yeah.
Wait, is registration?
All right, how's it going?
You should have checked.
Those are red Oreos, man. No thanks. Appreciate it
I'm
though.
not too sure.
Yeah, make my insides match. All right, any questions from what we've been doing so far? Aux said, PA5.
Are you okay?
Good to go? Good to go. All right, we're going to talk about system programming. We're going to start by talking about process. And I want to look at this from a bash perspective, and then Monday we're going to start looking at this from a programming perspective. But let's dig into processes in general. So here's my laptop. It's running Linux. It's doing a number of things right now. It's running this program called Kazam, which is my screen recorder, which is recording everything that's on the desktop. It's running Cheese, which is, capturing the document camera's output and displaying it here. It's listening for incoming email and recording that. It's monitoring the condition of my batteries and telling me that I'm at 100%. And if I unplug that, right, it will note that it's, eventually it will note that it's not plugged in anymore. It's monitoring the network and the signal strength and so on and so forth. So it's doing all these different things, right? And if you've done Engineering 270 and you think about a PIC processor, or if you played with an Arduino, single board processor, what is that? It's basically a CPU and a memory, and you throw instructions into the memory and the CPU grabs an instruction, executes it, grabs another instruction, executes it, just keeps doing that. That's the life of a CPU. Grab an instruction, do what it says, increment a register, check some value, shift something a certain amount, whatever, right? And it's really doing one thing at a time. When a PIC processor says increment file register 20, that's what it's doing. It's reading the contents of file register 20, it's sending it to an add unit, it's sending a 1 to the add unit, it's taking the output, it's loading it back into file register 20. So CPUs generally do one thing at a time. But my laptop is doing a bunch of things simultaneously. If I run the top command, I can see some of the things that are going on. But in the upper left here, it tells me tasks 278. There's 278 things happening on my laptop right now. And there's some of them. So we'll talk about how that happens in a moment. But let's think about processes. So the first command I want you to know about is PS. I don't even know what PS stands for. I think of it as process status, process snapshot. PS gives me 2 lines of output plus a header. It shows me 2 processes that are currently running, bash and PS. Okay, what is bash? Bash is this program that runs when we log into Linux and shows me a prompt in which me to type something and then executes something in response to that. PS is this command that we're talking about right now. And if I say PS, it shows me exactly 2 things happening on my system right now. The bash command and the PS command. And if I say PS again, I've got a bash command, I've got a PS command. Okay, so there's some information available on here. There's first column is process ID, PID, and the process ID of bash is 5182. It's a unique integer that identifies this process to the system. The PS command had a process ID of 5233. Well, now when I said PS again, my bash ID was still 5182, but my PS ID was 5237. It was different. And if I say PS again, my PS command has an ID of 5242. If I say it pretty quickly after that, my PS will be 5243.
Is that its position on the line?
It's basically just an ID that's used. It's like a student ID. We don't like dealing with names. So it's a numeric identifier for that process. And the value of it is essentially meaningless other than as a reference. Kind of like student IDs, the actual number doesn't really mean anything. It's just the next number that was available. Social Security numbers aren't like that, by the way. The number that you have for Social Security actually is derived from when you were given the ID and what state you were in. And it's only the last 4 digits that are random, which guess what? You've given everybody. So it's an identifier for that process. Now if I say PS-L, I can get more information about these commands. So I get a column called UID, that's user ID. Okay, my user ID is 1000. The PID is still the process ID, but I also see a new column, PPID, that's the parent process ID. And if I look at bash, its ID was 5240, or PS, its ID was 5245. Its parent ID was 5182. Guess what? That's the ID of bash. So the bash process is considered the parent of this PS process. Why? Because when bash was running, I typed PS enter, and bash said, oh, you want to execute the PS command, and it created a new process to execute PS. And that's the process we're seeing there. So the parent ID basically tells you where this process came from. TTY, that's the teletypewriter. That's the terminal associated with the process. Well, we don't have physical terminals plugged into the back of our CPUs anymore. So this is a pseudo terminal. So PTS is pseudo terminal, and PTS 0 is the one associated with this bash session, and thus with this PS. Time is the amount of CPU time this process has taken, and it's less than a second. That will slowly creep up over time. But these are the processes associated with the terminal from which I typed the PS command, sudo terminal 0. If I want to see all processes associated with me, I can say PS-U for user and type in my user ID, and I see a bunch more processes. Because, I opened a web browser somewhere, and when you open Chrome, it opens up, like 200 new processes to run Chrome efficiently, and so on. So let me hop onto the Linux server. So there's my PS, it's still bash and PS. If I do PS-user nick, there's 5 processes associated with my user ID. So the PS and the bash at the bottom as usual. Another process called SSHD. And if I look at my bash process, its parent's process ID is 56153. Well, that's the process ID of SSHD. Why did SSHD create bash? Because when I was on my laptop, I said SSH linuxengrcs.com, and that basically started a conversation with a process on the Linux server called SSHD. And it made a copy of itself, and then that copy created this bash process. And then there's some other processes out here that we're not going to worry about for now. So I logged into the Linux server. I've got 5 processes, 4 processes running, plus, if I use a command, the 5th process. If I want to see every process on the system, I can say PS-E, and there's every process. And there's things like Apache, which is serving up web pages. So when you go to linuxengrcs.com, you're talking to one of these processes that's saying, oh, you asked for, the syllabus for CSE224. and it finds it and it turns it into a pretty web page and it sends it back to your browser. And there's a lot of, most of these processes I have no idea what they do, but they exist for a reason, unless some of them are like, you know, hostile processes, and that could be, but it's not. So how many processes are running on our system? About 120 some. Right, I can just count how many lines ps-e gave me. And ps-el will give you more information, so you can see what process created some other process and so on and so forth. And you notice that a lot of these processes have a parent process ID of 1. 1 is the original process. That's how it got to be number 1. It's the first process created when the system boots, and it's basically responsible for creating all the other processes. Alright, so what does this mean practically speaking? When you type a command, date, and you hit enter, okay, right now bash is running. Bash is listening to standard in. Bash is noticing that I hit enter, and it's looking at what I typed, and it sees I typed DATE, and it says, oh, you want to run this program called date. It finds that program, it executes that program. That program will print out the date and time. That program exits, and bash says, oh, I'm done with that, and it gives me a prompt and waits for another command. Alright, so here's a simple little script that basically says enter your name, waits for me to type in a name, says hello, whatever my name is. So it says enter your name, I can put in my name, it says hello Nick. Okay, so I run the script, it says enter your name. Let me hop on to another account on the Linux server, and let me do a ps-user Nick. And I see my 4 processes as usual, including bash at the bottom there, but my bash process 56154 is the parent of another process 56231, which is running this script called SSS. That's what's running over here. And it's not really doing anything, it's just kind of waiting for someone to type in their name. So I can type my name, and now if I look at processes owned by Nick, that SSS one is gone. Okay, so life cycle of a process. Now suppose I am running this command, and it says enter your name. And I say delete all my files please, right? That is not something that bash sees. That is the input to this script, SSS, that was saying read name, and that just became the value of the variable name. If I'm sitting at my bash prompt and I say delete all my files please with typos or whatever, it'll say delete command not found, right? So when this command is running, anything I type that's standard in is connected to this process's input. Bash is not getting any of that. So look at the processes. Bash is still running, SSS is running, but SSS is the one listening to standard in. Question? Okay. So suppose I want to send a command to bash while this program is running. I want to know what the date is really, really badly. So I want to run the date command. Okay. I can suspend this process temporarily. And the way you suspend is by doing Control-Z, which you usually just write as a caret and a Z. So if I hit Control-Z, it prints out Control-Z, and it tells me bracket 1 stopped SSS, and I get my bash prompt back. Okay, if I look at my status, I've still got my 5 jobs out there. this SSS job, this column over here used to be an S. It got changed to a T. Okay, this is coded information about the state of my process. And right now, you know, if I say date, bash is listening to my input. So my program is still running, but it's kind of like off on the side right now. Yeah?
So is there a way I can test this offline with two different terminals? Or
You could, yeah.
yes, is the command still the same as the PS?
Mm-hmm. Yeah, you can log into the Linux server a few times.
Do I have to log into the Linux server to use this command?
You don't have to, no. You can do it. Do you have Linux on your laptop?
Yeah.
You should be able to do it from there.
Yeah, so I have the Visual Studio Code terminal and the Ubuntu. How would I go about?
Are you at a Linux prompt right now?
Yeah.
So if you just type PS enter, it should show you.
Yeah, it shows me what's going on right now.
Yeah.
But how would I run my program and then monitor what's going on?
Can you open a second terminal?
Yeah.
So if you open a second terminal and you do PS-U username, it should show you all the stuff that's running.
So it's everything's happening on.
Yeah.
Oh, okay. Cool.
All right, so Control-Z suspends the process, okay? It basically says, stop what you're doing, go hang out on the side for a while, and my standard in is connected back to my bash script. Now, if I want to continue running that thing that I suspended, I can do that with the command FG. So that says bring the job back to the foreground, which means listen, roughly, it means listen to standard in, or listen to the keyboard. So if I say foreground, now my program is running again, and if I say date, right, bash doesn't show me the date and time. Date was the input to the script, and it says hello date. And then it exits, and so if I look at PS, I don't see that program running anymore. And if I want to start a program in the background, I can do that by saying program name followed by an ampersand. So that's just like running the program and then doing a Control-Z. Almost. So this is useful if you have some program, like your program is going to do something on War and Peace, and it's going to count the number of vowels or something, and it's going to take 5 minutes to run. And while it's running, you still want to be able to be editing your next program or doing something else in bash, right? You can run your program with an ampersand, which runs it in the background, and bash is still listening to standard in, and you can still go in and edit and things like that. And then I can bring it into the foreground with an FG command and continue executing that. All right, so here's another script called delay. This sleeps for 15 seconds and then it says hello. I'm going to change it to 10 seconds because life is too short. All right, so I run delay and it'll sit there and hang out for 10 seconds and then say hello, and then it'll exit. Here we go. Okay, suppose it's running and I hit Control-Z, which stops it. Okay, I can wait 10 seconds, it's not going to say hello. Because the job is basically suspended. It's frozen. It's still out there, right? Delay is still running. And this process delay, 56305, created a new process, 56306, which is executing the command sleep, which was, you know, the first line of my script. And 10 seconds have already passed, but because everything is suspended, it hasn't noticed that 10 seconds has passed and it hasn't said hello. So if I say foreground to bring this into the foreground, it immediately says hello and the program exits. Now when you say Control-Z, that really says suspend the process. And it doesn't kill the process, right? Control C kills a process. Control Z just kind of stops it and puts it in suspension. FG will bring it back to the foreground, but I can also say BG, which says run a suspended job in the background. And that's really what an ampersand does. Command ampersand says run command in the background. So I can say delay, I can control Z it to stop it, I can say go ahead and run that in the background. And then I can go ahead and I can do whatever I want to do. I can hop into VI or whatever, but that command is still running in the background, and after 10 seconds the sleep expires and it says hello.
Oh, crazy.
Yeah. And then when I come back to bash, it tells me that job finished, it's done. Delay. And if I type something like date and I run that in the background, right, it shows me it created a process 56323 that's running in the background. It came back and gave me my bash prompt 5028, and then the date command executed and printed out the date. And now date has exited, but it's not going to tell me until I hit enter. And then it'll say, oh yeah, by the way, that job is done. So I've just thrown 3 jobs into the background, delay, delay, and sleep 2000. And the first 2 finished. And if I hit enter, it'll tell me those are done. Let's throw some more sleeps in the background. So I've got a bunch of jobs going on right now, right? They're all in the background. What I type is still being listened to by bash. So I can use the command jobs to see what jobs I have. So jobs is a lighter version of PS that basically shows you jobs that you've created and are running in the background. So I have 3 jobs 3, 4, and 5. And so these commands like foreground and background, I can say % job number if I want to refer to a particular job. So I could say let's foreground job 4, and now bash is executing the command sleep 1000, and anything that I type is being listened to by that sleep command. And if I suspend that, I can say control Z, that's stopped. Now if I say jobs, notice what's happening. Jobs 3 and 5 are still running, job 4 is stopped because I control Z'd it. I can say let's throw job 4 into the background, and now job 4 is also running.
What if the pluses and minuses then?
If I say foreground, I think it'll foreground the one with the plus on it. And I don't know what the minus is. I think it's a rudimentary prioritization. So we can have multiple processes running. We can bring a process to the forefront by saying foreground with the % process number. We can suspend it with control Z. We can put it in the background by saying background % process number. Or we can start a job running in the background by putting an ampersand after it. So we have a fair amount of control from bash over processes. So the other thing we can do is we can kill processes. So I've got these things sitting out here running, and maybe I don't want that last one that's sleeping 1500 seconds. I can say kill %5, and that terminates it. And now if I say jobs, I've only got those 2 other jobs running. And I can say kill %3 and get rid of that one. Or I could foreground this job and then just control C, and that'll also kill it. And now I've got no jobs hanging out in the background. Unemployed. So there's also this kill option. So let's start a VI session in the background. So I'm going to say VI funny and do that with an ampersand. Okay, so that stops immediately because VI really wants the connection to your keyboard because it's an interactive editor. So it stops if it doesn't have that. So there's my VI process, 56384, and it's process 1. And I can kill %1, but it didn't die. Now when I killed my sleeps, it said terminated. When I killed my VI process, it just said stopped, and it's still out there.
Kill it again.
Alright, so I can't kill it. So here's the thing, kill does not actually kill a process. It's a little misnamed. Kill is really used to signal a process. And we're saying, would you please kill yourself? And VI says no. Doesn't want to do that. But the sleep command was like, yeah, what the heck, I'm just sleeping. So if you look at the manual page for kill, you see hold on, I got the option wrong. -L. If you say kill -L, you get this funny little list of cryptic names. These are different signals that we can send to a process. So kill doesn't actually kill the process. All it does is it sends a message to the process, and it's a very short message. It's a single number. It sends a signal to that process. And to some degree, the process gets to decide what to do in response to that signal. So sig int, signal 2, is used to interrupt a process, something like Control-C perhaps, right? Which, you know, if you're inside VI and you hit Control-C, it doesn't actually exit VI. It gives me a message saying type : quit enter to exit Vim, right? But I can be typing stuff, and when I hit Control-C, it just takes me out of insert mode, and then it tells me how to quit if that's what I'm trying to do. But most jobs, if you hit Control-C, the process exits. Sig hup, signal 1, hup is short for hang up. That's back when we used to have modems, telephones connecting computers together, and when you were done talking to a computer, what do? You hang up the phone, right? Well, when the phone gets hung up, the other side would be sent a sig hup signal saying the phone has been hung up, and it would go ahead and log out the user and so on and so forth.
Do we still use that?
Sig hup is still used. Yeah, you can still hang up buddy sessions and stuff. It's all emulated. Sig power 30 is presumably related to a power condition. If the power starts dropping, if the voltage level drops below a certain amount, a process may get a sig power signal to respond in an appropriate way. Sig seg v, signal 11, seg v as in segmentation violation.
These are like flags.
These are like flags, yeah. So if your program tries to access a memory location that's not available, how do things happen after that? Well, the hardware system that manages the memory will cause a signal to be generated saying this person tried to access memory that's not available, this process, and the process basically gets a sig seg v, and that leads into this segmentation fault. So signal 9 is sig kill. That's the one that actually kills a process, and that cannot be blocked. Okay, so I've got VI running there. So if I say kill -9%1, that actually kills it. And And now if I look at jobs, there's no VI running. Right? And if you kill a VI session that's running and you're in the middle of editing, then the next time you try to edit it, you get your annoying message about the swap file. Right? Because when you :WQ to get out of VI, it gets rid of this file saying, okay, this person's done editing it. Well, this file was there while I was editing it, and then I killed the editing session, so that file is still there. That's exactly what that file is for. All right, so we can signal processes using kill. There's one other I wanted to mention in here that looked interesting. Oh, FPE. So SIG FPE is probably a floating point exception, division by 0, for example. All right, because when you divide something by another thing, it would be inefficient if every time that you did that, the CPU had to check, is this thing equal to a 0 on the bottom? And if it is, how is it going to cause your program to print out, floating point exception division by 0? So it throws a signal. And your program is set up so that when it gets that signal, it says, floating point exception divide by 0. All right, so here's a cool little program called burn. This just burns your CPU. So it's 1,000,000 loops containing 1,000,000 loops containing 1,000,000 loops. So this will run 10 to the 18th loops, and it just keeps incrementing a variable called sum. So right now on the Linux system, there's not a whole lot going on. The load average on the top is pretty much 0. Okay, that's a dead system. Load average, the first 0 is sort of the current load average, and then there's I think a 1-minute average and a 5-minute average or something like that. And the lower those numbers are, the less the system is doing. Now it's got 129 tasks, right? We see that up here. It's using 150 megabytes of memory. Sorry, 150 kilobytes of memory. 150 meg, this many kilo. But it's not really taking a lot of CPU time. So it just went up to like 0.07. Very small load. So I'm going to run this program in the background. And I've still got Bash's attention. But if we look at this top display right now, this command burn is the top CPU user, and it's taking about 96% of the CPU, 99.7%. And our load average is creeping up. It's 0.38, and it's up to 0.43, and so on. So the Linux server, linuxengrcs.com, is really spending its whole time right now executing my nested for loops. Right, that's what it's doing. But if you're logged in, you can still type and it responds to you. And I can come over here, since I ran that in the background, and I can look at my files and I can edit files, and there's no noticeable delay. But it's still spending almost 99% of its time running my code. Okay, so this is the multitasking aspect. This is the way it's doing multiple things at once. So I can make a copy of my executable and run that in the background. And now I've got two things chewing up my CPU, burn and burn 2. And they're taking about 50% of the CPU each. And I can do that a few more times. Now I've got 10 processes out there, and they're each getting 10% of the CPU. This is pretty efficient. Most of us, if we try to do 10 things at once, it doesn't take us 1/10 as long. It takes us possibly longer than doing them one at a time, because we're not good at jumping from one thing to another. But this is really efficient multitasking. And so the time column is showing CPU time. And it's creeping up slowly, but you know, at 1/10 real time. So every 10 seconds, that time will go up by about 1 to the left of the decimal point. All right, so I can kill some of these. All right, so I got rid of 5 of them. And these jump up to 20% CPU each. What happens if I log out? While those things are still running. And they don't show up under my jobs anymore because they're no longer associated with my current terminal. But if I do a ps-user nick, I can see them. So just because you log out doesn't mean that your jobs go away. Now sometimes they do, right? But a signal is sent when you log out, and some commands respond to that by exiting, some don't. This burn command is just a program, a bunch of nested loops. It has no reason to exit, and so it's still running. And Rogue does this sometimes. Every now and then I do a top and there's a Rogue that's like 5 days old, just chewing up the CPU, so I just kill it. So how do we get rid of these? So we can use the kill command, but we can also use a process ID instead of a %. So I can kill 56621, and now one of those has gone away. And I can kill 22, 23, 24, 25. Right, and those should go away. And our load average was up to 4.6 something, and that'll start dropping pretty quickly now because nothing's really chewing the CPU. And now if I do my PS again, I've got my usual bash related jobs. So back on my Linux machine, there's a fair amount going on here. I got 278 tasks out here. I have this command called Kazam, which is taking about half my CPU. That's the screen recorder. I've got Xorg, which is managing my display, Pulse Audio in case I'm doing some music playing and so on, Cheese, which is monitoring the document camera, Chrome, which is Chrome, right, and there's multiple versions of that, and there's lots of stuff going on my system.
Daemon on there.
And a daemon.
Several.
So if I run my burn command in the background, burn jumps up to taking 100% of the CPU. Kazam is still getting 34% of the CPU. So those percentages add up to more than 100. Why? Because I've got multiple cores on the CPU. So Linux and GRCS-COM single core machine. This one has multiple cores. So I can run 3 copies of my CPU burner, and they each get about 100% of the CPU. And then Kazam gets 40% of the remaining core, and the other stuff split the difference. But if I run another version of this, so I've got 5 processes that are vying for the CPU, they all get about 90%, 80%. So you can deduce from this I've got 4 cores on this machine. And if I have 4 processes running, they can each get 100%. And that works fine. But once I have 5 processes, that are after the CPU, they have to share. And so they each get less than 100%. And if I keep doing this, right, then the percentages just go down. So now they're all getting about half the CPU. And up here, in addition to telling me I've got 285 tasks, it tells me 8 of them are running, 229 of them are sleeping. Right? Most of the time, nothing is actually running on the system. Everything is kind of hanging out, waiting for stuff to happen. Except these programs, which are totally CPU bound. Right? If you look at the assembly language, it's like a pick program. It's just a bunch of executions inside loops, branches, right? There's no reason they would ever not want to use the CPU. So those are always in a running state. But most of the jobs out there are sleeping. So I can kill all of those, and now we're back to 1 running process, 229 sleeping. No zombies. And our load average is dropping quickly. So load average, it's a relative figure, but if you see it above like 3 or 4, there's something heavy going on the system. If it gets up to 5 or 6, you're probably going to notice a slowdown. But typically it's smaller than 1. Yeah?
So if a program is constantly looping and you stick it, make a cube, make a wait kind of function that sticks into like a while loop, is that ever going to be considered as sleeping?
Yeah, so let's do a get car the first time that we go through 1,000,000 of these things. Right, so it already hit that state where it was waiting. So I've only got 1 thing running, 2 things running, probably top and Kazam. And this already went into its stop state. But you could set up a little delay so that it, loops for 10 seconds and then tries to read a character, and you'll see the state change from running to waiting after 10 seconds.
Is the loop a specific feature built into the chip?
No, it's really just that if
No,
you...
Not loop, I'm in sleep.
Right, so here's the assembly language version of that program, and it's really just it starts off, it jumps down to L2. L2 compares something to 1,000,000, and if it's less than or equal to it, it goes back up here to L7, which jumps to L3 and compares something and jumps up to L6, and that jumps to L4 and compares something and jumps to L5, which does your increment to sum, and then it comes back in here. And all of these instructions, they do something and they move on to the next instruction. Right? It's an assembly language level loop. It's not that the loop is special somehow, it's that there's no point in here where it says something like, let me know when the mouse button gets pressed. Now this call to get car, right, that starts executing a series of code which eventually does say, let me know when an enter key has been pressed. And it goes to sleep and waits for notification. Right, so it's really the fact that you're not doing input and output that makes this thing CPU bound.
But not all chips have a sleep feature, right? You can't just program.
It's really a feature of the operating system, though.
Okay.
So that's kind of where we're going with this, right? Is that it's really the operating system that's doing all of this for us. The CPU just executes commands, and the CPU is always executing stuff. Most CPUs, you can put them to sleep, but you don't, right? When you suspend your operating system, it'll actually put the processor to sleep sometimes. but I'm sitting right here, nothing really needs a CPU. It's still doing things, right? It's mostly executing a process that just says, you know, loop, branch to loop.
So how does this work for like devices like Bluetooth? There's no operating system on them.
Devices like what?
Bluetooth?
Well, so if you have like a Bluetooth headset, right, there is some sort of CPU in there, and it's executing code that's waiting for, you know, a packet to come in or something to transmit or something like that. Other than power saving features, it's really doing the same thing. It's always executing an instruction. And most operating systems, if you look in the right spot, eventually you'll find something like this, right? The thing we put in our 270 programs. Something that just says, you know, just spin your wheels, just hang out here and wait. And it's waiting for an interrupt. And when you click a mouse button, when you type a key, those generate interrupts. And the operating system says, hey, you know, got a character for you, wake up, here you go. And then when it's done, it comes back and it just spins its wheels. All right, so that's a little bit about how we manipulate processes and look at processes from a bash perspective. What I want to start doing on Monday and Tuesday is look at this from a programming perspective. So we're going to go into C and we're going to look at how we create processes, how we manipulate processes, how processes can be communicated with, and so on and so forth. So we'll start that on Monday, and that's fun stuff. All right, so I will see you next time.
Hey Nick,
Yeah.
have you ever looked into